Hi friends, so today we look at physics topic which is light, reflection and refraction. So question number 1, how does light enable us to see objects? So assume that we have a light source like the sun here, right? And assume we have an object, a red apple with a green leaf, okay? So what happens is the light falls on the object and gets reflected, okay, and what the light gets reflected that goes into our human eyes, goes to the retina, and our brain processes that signals, and that is how we see the objects. See, the green leaf appears green because it reflects green color and absorbs the rest of the colors. Similarly, the apple seems red because it reflects the red light and absorbs the other part of the white light. Okay, so light from source reflects off of the surfaces and reaches the eye, where it is processed by retina and the brain, and light travels in straight lines. So you can see the straight line mathematical model of the light, and surfaces appear the color that they reflect. Okay, what is reflection? When any ray of light hits a reflective surface, it bounces back, and that is called as reflection. Okay, so if you look at this diagram, we have created a line, right? And the top surface is reflective and the bottom surface is opaque. So opaque surfaces are shown by these small dashes here, right? So the bottom surface is it is non reflective. Only the top surface, which is smooth, is reflective. Okay, the bottom surface is opaque. So when a ray hits this surface like this, it bounces back. Okay, it bounces back, and this process of when a ray hits a reflective surface, the process of it bouncing back is known as reflection. Okay, so this ray is the incident ray which hits the surface, and this ray which gets reflected is the reflected ray. Okay, and the reflection is around a vector called the normal, okay, which is perpendicular to the surface. So it is at 90 degrees. This normal is at 90 degrees to the surface. We have to remember that. Okay. So what is refraction? When a ray of light hits a transparent surface, not reflective in this case, it hits a transparent surface, the direction of propagation of the ray in the second medium, that is the transparent object, changes due to change in velocity of the light. This process is called refraction. Okay. So here again we have shown a picture. We have a surface. On the top of the surface we have the air, and below the surface we have the water. Okay, so basically this surface is the surface which separates the water and the air. So let's assume that an incident ray is coming and hitting at this point. Okay, we have also drawn the normal here, which is at 90 degree to the surface. You can see the dotted line and the 90 degree angle notation. Now this ray, instead of going straight along its path, right, because of the process of refraction, changes its direction. Okay, the reason why it changes its direction is that the velocity of the light is lesser in water than it is in the air. So because of this change in velocity, there is a direction change, and this process is known as refraction. Okay, what is diffraction? Okay, when the light interacts with very small objects, very small, almost the size of human hair, or very close to molecular sizes, the light behaves like a wave bending around small objects. This process is known as diffraction. Okay, now next question is, state the laws of reflection. The law of reflection says angle of incidence is equal to angle of reflection. Okay, again consider this surface. It is reflective on the top and opaque on the bottom. Okay, here's the incident ray AO. Okay, and it gets reflected like OB. Okay, that is the reflected ray. Now what the law of reflection says, that angle AON, where N is the normal, the angle AON, which is the angle of incidence. Okay, angle of incidence means the angle that the incident ray makes with the normal. Okay, is equal to the angle of reflection, which means angle AON is equal to angle NOB. Okay, NOB is the angle of reflection because that's the angle the reflected ray makes with the normal. So law of reflection says that the angle of incidence is equal to angle of reflection. Okay, and that's what we have written here. Angle AON is equal to angle NOB. Angle AON is equal to angle of incidence denoted by I, and angle of reflection is R denoted by R, and I is equal to R is what the law states. Okay, and the second point it states is this incident ray, the reflected ray, the point of incidence, which is the point O where the incident ray hits the surface, the normal, all these are in the same plane. Okay, that is the second point the law of reflection makes. Okay, next question, how is image formed in a flat mirror? Okay, we are not talking about curved mirrors still, we are talking only about flat mirrors. And what are the properties? Here we are showing you a flat mirror. This is available in any home. So in the morning, if you wake up, take a bath, and you want to comb your hair, you'll be looking into the mirror. That's a flat mirror, right? So in flat mirror, what happens is any ray which falls exactly perpendicular to the surface will get reflected back as is, and it appears to be coming from some point. Okay, and any ray which hits the surface at an oblique angle to the normal will get reflected, so that the angle of incidence, which is this part, is equal to the angle of reflection, which is this angle, right? So if you trace back this ray, it appears to be coming from the same point. So this point is nothing but the image of point A. Okay, this image is at the same distance that the object is from the flat surface. Okay, so the farther you go, the farther image goes. The closer you come, the closer image also comes. Okay, so the object distance is equal to image distance. That is, the distance of the object from the surface of the flat mirror is equal to the distance of the image from the flat surface. Okay, and it is laterally inverted. That is, your left becomes your right, your left becomes the right of the image, and your right becomes the left of the image. So it is laterally inverted. Okay, so now let's look at curved mirrors. Okay, so the question is, what is a spherical mirror, what is a concave mirror, what is a convex mirror, and what does the pole of the mirror mean? Okay, what is the center of curvature mean, and what does the principal axis, what are all these terms mean? To explain all these terms, we have drawn a sphere here. If you can see that the sphere has been drawn in a very light manner, because what we want to show is whether it is the concave mirror or whether it is the convex mirror, both are type of spherical mirrors because they are part of the sphere. Okay, their shape is such that these mirrors can be considered a part of a sphere. I repeat again, spherical mirror has two types, the concave mirror and the convex mirror, and the spherical mirror is called spherical because it is a part of an imaginary sphere which has a center, which has a radius and all that. So the mirror is a part of a sphere, that's why we call it spherical mirror. Okay, now what is concave mirror? Concave mirror is where the reflective part is on the inside. It's like in the cave, right? That's why it's called concave. It's called concave because the reflective part is on the inside, and the opaque part, that is the non-reflective part, is on the outside. Whereas for a convex mirror, the reflecting part is on this side, the outside, and the opaque part is on the inside. So that is the difference between a concave mirror and a convex mirror. Okay, and you can see there is a point right at the center of this mirror, whether it is the convex mirror or the concave mirror. In case of concave, O2, and in case of convex, O1, these points are what is known as the pole of the mirror. Okay, and since this mirror is nothing but a part of a sphere, imaginary sphere, that sphere will have a center, right? That center is nothing but the center of curvature. Okay, and since it is a sphere, it will also have a radius, isn't it? So that radius, which is starting at the center and going to the pole, Okay, so CO2 equal to CO1 is the radius of the sphere. Okay, and this line which cuts through, joins, passes through the center of the mirror and passes through the center of the sphere, that is known as the principal axis. Okay, this line which passes through the center of the sphere and the center, that the pole of the mirror which is at the center of the mirror, that is O2, CO2, the line which passes through CO2 is called the principal axis. Okay, what is the aperture? So aperture is the diameter of the mirror. Okay, so it is the length between M and N, point M and N. Okay, similarly the aperture of the convex mirror is the distance between M dash and N dash. Okay, this is what is known as the aperture. So whenever we study about the mirrors, we will be considering mirrors with small apertures. That is what we have to understand. Okay, so next question: how do parallel rays interact with concave and convex mirrors? Show the ray diagram, and what is the principal focus point and what is the focal length? Okay, so if you consider a concave mirror first, you can see that AB is a ray which is parallel to the principal axis CO1. Okay, so what is happening is, because it hits it at B, okay, and C1B is the normal at that point, the angle of incidence is equal to angle of reflection, so it gets reflected in the direction of BC. Okay, AB, which is parallel to the principal axis, get reflected in the direction of BC. Similarly, DE, which is also parallel to the principal axis, and the normal here is C1E because that is the radius of the sphere. So DE will get reflected in the direction of EG. Okay, and these two guys will meet at a point which is known as the principal focal point. Okay, so the answer to the question is, parallel rays get converged. You can see the convergence happening. See, these two guys are parallel, AB and DE are parallel, but once the reflection happens, they both intersect. That is, the reflected rays converge at a point F. That point is called the principal focus point, and it is denoted by F1, and this is the point which I am pointing out. Okay, in case of the concave mirror. So what is the focal length? The distance between the pole, which is O1, and the principal focus, which is the F1. O1 F1 is called the focal length. Okay, and as we know, the radius is nothing but the distance from center to the pole. Center is C1, pole is O1, so CO1 is the radius of curvature. Okay, what happens in terms of a convex mirror? Okay, in terms of convex mirror, see, the ray is coming like this and it gets reflected, it gets diverged. You see this, AB is getting reflected along BC and DE is getting reflected along EG. So whatever was parallel is now getting diverged like this. It's not converging, it's diverging. But it is diverging, it seems as though it is diverging from a point called F2. You see that? Because if you take the diverging reflected ray and you backtrace it, it will come to this point. If you take this ray which has been reflected and you backtrace it, it is come to the same point. So it seems like it is diverging from this point, which is nothing but the focal point. So parallel rays get diverged and appear to come from the principal focus point F2 in case of the convex mirror. So O2 F2 is the focal length. Okay, here O1 F1 was the focal length. Okay, here O2 F2 is the focal length, and C2 O2 is the radius of curvature. Okay, so check out both concave and convex mirrors. In case of concave, it converges to the focal point. In case of convex, the parallel rays diverge, but they diverge in such a way that they seem to be diverging out of the focal point. Okay, see, there is nothing behind the mirror. Okay, so in this case the focal point is in front of the mirror, but in this case, in case of the convex, the focal point appears as though it is behind the mirror. Okay, it's imaginary. Okay, it's not physical. Only the front of the mirror, the space is there. Behind the mirror, there is no space. But the focal point is imaginary because the diverging rays appear to diverge out of the focal point in case of convex mirror. Okay. Next question. How are the radius of curvature and the focal length related? So we can show that the radius is always is equal for mirrors of small apertures. We can show that radius is approximately equal to 2 times the focal length. So R, that is the radius of curvature, in this case C1O1, okay, is twice O1 F1. Okay, here the radius is C1O1 and the focal length is F1O1. So R is always for small apertures 2 times the focal length. Radius of curvature is 2 times the focal length.